So let's investigate the physics of reflex motion. We have a star and we have a planet. And we'll make the assumption that the planet is much smaller than the star, which is virtually always a very good assumption. So the star will have a mass m star and the planet will have a mass m planet. Now they're both going to move around their common center of mass. So that's the common center of mass. The star will move in a circle of radius r star, and the planet in a larger circle of radius r planet. Notice the r planet and r star are not the size of the star and the planet, it's how far they are from the center of mass of the whole system. And they'll both be moving with some velocity, let's say v star here and v planet there, and they'll both go in a circle. So that's our situation. What can we actually derive about this? Well, there are three constraints we can put. The first is that they must be moving around their common center of mass. The definition of the center of mass tells you that m star times r star equals m planet times r planet. That's just a definition of center of mass. So what this is telling you is, as the star weighs much more than the planet must be much further away than the star to balance out. If the two are equal mass, it's like a binary star, two stars, then both orbit around a point midway between themselves. As the planet gets smaller and smaller, the center of mass moves closer and closer to the star. So that all makes sense. But that's not enough by itself. A second equation we can get comes from the nature of motion in a circle. For anything to move in a circle, there must be a force, a centripetal force towards the center, which is enough to keep it going in a circle. And the equation for centripetal force is that it's equal to the mass, in this case of the star, times the velocity of the star squared over the radius of the circle it's moving in, mv squared over r. And that's the general equation for centripetal force, whether it's a car speeding around a circle or a planet in orbit around a star. So there must be a force towards the center of the size acting on the star to make it go in a circle, otherwise it would keep going in a straight line or fly off on an ellipse or some other path. And that must be supplied by gravity. So gravitational force given by Newton's law of gravity, g m star m planet over the total distance between them, which is r star plus rp all squared. And that's also equal to the centripetal force of the planet, because the gravity works both ways. It's the gravitational pull of the planet on the star and the gravitational pull of the star on the planet. So that's also got to be what keeps the planet in its motion. So it also equals mp vp squared over rp. So that's our second equation, which we get from saying that gravity is supplying enough force to keep things moving in a circle. And there is one more equation we can use, which is often we won't measure the velocity, we'll measure the period. So we might want to relate velocity to period. Now if something's moving in a circle, the distance it has to move is the circumference, which is 2 pi r. And if it's going in v, the time it'll take is just equal to 2 pi r over v. And the time taken to go in a complete circle is just the period. So we have that the period is equal to 2 pi, say r of the star, over the velocity of the star, or equivalently 2 pi radius of the planet over the velocity of the planet. Okay, so those are our three equations. Now let's use them to derive something in a system like this.